We present an architecture for reactive mobile manipulation on the move. Our architecture enables a mobile manipulator to perform pick-and-place tasks without ever coming to a stop, which can significantly reduce total execution time for multi-step tasks. The closed-loop, reactive nature of our method enables the robot to robustly grasp unpredictably moving objects while on the move, a task which is impossible with existing planning methods. Existing approaches to manipulation on the move typically rely on generating planned trajectories, which means they are highly dependent on accurate perception and precise execution of the trajectory. Here, unexpected motion of the mobile base causes a desynchronization between the planned motion for the arm and the base, resulting in a failed grasp. Our goal is to develop a system that is robust to imprecise robot control, perception errors, base disturbances, and unexpected object motion. We present a generic reactive architecture with closed-loop control that can perform reliably under these conditions, while still performing tasks on the move. We define a set of modules and interfaces that form a manipulation on the move controller. We present an example implementation for performing pick-and-place tasks with a wheeled mobile manipulator. The base controller computes a closest approach pose that smoothly connects the current pose with the drop point. With the closest approach pose determined, the robot is guided to that pose by the control law shown. These computations are repeated in real time to enable reactive control and robustness to base disturbances and inaccurate control. The reacher module ensures the gripper arrives at the object synchronized with the base motion. An analytic minimum jerk trajectory is generated for the end effector. This trajectory is fast to compute and is updated in real time, which enables the robot to react to imprecise control, as well as unexpected base or object motion. The desired end effector velocity generated by this module is translated into joint velocities by the redundancy resolution controller, which further ensures synchronization between the arm and base. We compare with two baselines. The first is a reactive method which treats the pick and place as separate tasks. The robot drives directly toward the object, stops to complete the grasp, and then drives on to the drop location. The result is a reliable but slower mobile manipulation system. The planned baseline generates a complete trajectory for the task, but does not update it. This baseline performs the task on the move, resulting in significantly reduced task time compared to the reactive baseline. However, the performance of the planned baseline is brittle. Inaccurate perception of the object or imprecise execution of the generated trajectory can result in failure. By comparison, our approach is able to reliably grasp the object while operating at even higher speeds than the planned baseline. For the dynamic object case, the results are similar. The reactive baseline reliably completes the task, but takes a long time because it stops at the object to complete the grasp. The reactive controller successfully completes the task in all 10 trials. The planned baseline is unable to successfully grasp the moving object in any of the 10 trials. This is expected. The object has moved since the trajectory was generated, and therefore it is no longer valid. Again, our method reliably grasps the object while operating at high speeds. Reactive control enables reliable grasping of the unpredictably moving object. To summarize, with a direct comparison of the methods, our approach efficiently and reliably completes the task, where the planned baseline is unable to do so, and the reactive baseline takes significantly longer. The resulting motion is smooth and graceful. Even faster grasping is possible by allowing relative motion between the gripper and object at the moment of grasping. We also consider a long horizon task, where the robot must grasp and transport 10 objects from one place to another. The reactive architecture enables fluid motion and never needs to stop and plan the next part of the task. At a base speed of 0.4 meters per second, our approach averages a round-trip time of 18 seconds, and did not produce any failures over the 60 real-world trials. This represents a 38% improvement over an existing state-of-the-art method on a similar task. The architecture is demonstrated here on 3 different robots, with varying degrees of freedom. The architecture required only minimal modifications to the redundancy resolution module to work on these platforms. In the future, we are working towards increasing the capability of our system and enabling reliable performance in more challenging environments. For example, including reactive obstacle avoidance enables efficient pick and place in environments with dynamic obstacles.